Every piece of geological evidence you have ever trusted to answer this question is hiding something it cannot tell you. Not because geologists are wrong, because the planet destroys what it cannot use. It compresses civilizations into chemistry, melts continents back into magma, and delivers what survives to the future as a thin chemical stripe in a rock wall. 3 centimeters, maybe 4. The researcher marks it. She labels it volcanic. She moves on. In 2018, a NASA director and an astrophysicist published a peer-reviewed paper in the International Journal of Astrobiology. They were not asking whether ancient astronauts existed. They were not searching for Atlantis. They were asking a specific quantified scientific question. If an industrial civilization had operated on this planet 50 million years before us, would any physical evidence of it survive to the present day in a form we could identify as artificial? They ran the numbers against the actual mechanisms of geological preservation. They did not find evidence of a prior civilization. They found something that in its own way is stranger. They found that we would not be able to tell. The geological record cannot answer this question. Not with the tools we have. Not at the timescales that matter. That is what the Silurian hypothesis actually says, and that is what makes it worth spending tonight with. If this is the kind of content that stays with you, a subscription or a like helps this channel keep making it. It takes 1 second, and it matters more than it sounds. The rock record is not a library. It is an incinerator with very specific tastes. Here is the thing most people believe without knowing they believe it. When geologists say no evidence of a prior civilization has been found, most listeners hear the record is complete, and it shows nothing was there. This is not what the sentence means. What it means is, in the fraction of the record that has been examined, interpreted through a framework that does not include industrial civilizations as a possible cause of ancient chemical anomalies, nothing has been found. Those are not the same claim. The gap between them is where tonight's question lives. Start with what the geological record actually preserves. Not species, not organisms, not populations. Accidents. Accidents. The fossil record captures less than 1% of all species that have ever lived. Not 1% of individuals. 1% of species. The rest are gone without a trace, as completely as if they never existed. Entire branches of the tree of life have been inferred only from genetic shadows in modern organisms, because nothing physical remains. Fossilization requires a specific sequence of events in the right order, with the right timing. The organism has to die in or very near water-deposited sediment. It has to be buried quickly enough that scavengers and bacteria do not disassemble it first. Soft tissue almost always goes regardless. Bacteria digest it long before mineralization can begin. What sometimes survives is bone, shell, tooth, woody plant tissue. And even that requires the surrounding sediment chemistry to cooperate without interruption for thousands of years. The right mineral saturation, the right pH, the right pressure gradient. Most of the time, one condition fails and the hard parts dissolve with everything else. The Cambrian Ocean was full of life 540 million years ago. We know this because a handful of exceptional fossil sites preserve soft-bodied creatures with unusual fidelity. The Burgess Shale, the Chengjiang Biota, sites where fine-grained mud sealed organisms so quickly that gill filaments and gut contents survived as two-dimensional impressions. These are accidents. For every Burgess Shale, there are 1 million locations where every organism that ever lived there vanished without leaving a mark on the record. Now think about what this means, not for organisms but for structures. Gavin Schmidt and Adam Frank, in their 2018 paper, calculated the time scale at which physical structures become geologically unrecognizable. The number is 3-6 million years. That is the window before the built environment, regardless of its material composition, degrades below the threshold of confident artificial identification in a standard geological survey. Not gone at the molecular level. Unidentifiable. A geologist pulling a core through what was once a city street, 4 million years after that street was paved, finds altered sediment with unusual mineral chemistry. She does not find a road. The road has been processed out of existence by the ordinary operation of the planet. 3.6 million years. The entire genus Homo fits inside that window. Every human ancestor that walked upright and shaped stone and eventually built cities lived within 3-6 million years of the present. If something existed before our genus appeared, the planet has already closed the file on its physical structures permanently. This is where most people instinctively reach for underground infrastructure. Subway tunnels, buried foundations, landfills. The logic makes intuitive sense. Things below the surface are protected from erosion. The intuition is correct and insufficient. Underground structures are subject to groundwater chemistry. Every aquifer is a slowly moving chemical system that dissolves, reacts with, and carries away material from everything it contacts over geological time. Steel reinforcement oxidizes and dissolves. Concrete undergoes carbonation and sulfate attack, accelerated by constant groundwater contact. Plastic components degrade chemically. The void spaces left by tunnels and caverns collapse as surrounding material creeps inward under lithostatic pressure that increases with depth and time. What remains is not a structure. It is a chemically altered zone in the surrounding rock with unusual mineral concentrations and no remaining geometry. The geometry is gone. Only the chemical shadow remains. The landfill question is worth its own moment. Modern engineered landfills are designed with a specific goal: contain the waste for as long as possible, manage the byproducts, prevent contamination of surrounding groundwater. From an engineering standpoint, they are some of the most deliberately durable structures we build. Compacted clay liners, leachate collection systems, gas capture infrastructure, decades of engineered containment for material that would otherwise decompose and disperse immediately. From a geological standpoint, they are among the least durable things we build. At geological timescales, the organic content of a landfill decomposes into the sediment organic carbon pool. The metals oxidize back toward their original mineral forms or dissolve into groundwater and redistribute through surrounding sediment. The clay liners, which are the primary containment mechanism, compress and crack under lithostatic pressure over millions of years and allow the contents to mix with the surrounding rock matrix. The glass devitrifies. The plastics degrade as described. What remains is a zone of chemically anomalous sediment with elevated trace metal concentrations and unusual hydrocarbon chemistry. Natural concentration processes, hydrothermal venting, evaporite deposition, diagenetic metal redistribution produce similar anomalies. The landfill signature survives, but it is not a landfill signature. It is a chemical anomaly that a competent geochemist would begin interpreting through the framework of natural concentration mechanisms, because that is what the evidence looks like. The preservation contrast between our civilization and the asteroid impact is the clearest illustration of the fundamental problem. The asteroid delivers iridium, rare in Earth's crust, globally distributed, chemically stable, with no natural source that produces a sharp global spike. Every feature of the iridium anomaly distinguishes it from background. Every feature is present exactly where the impact hypothesis predicts it should be. The signal is decisive. We produce carbon. We produce nitrogen compounds. We produce glass spheres and polymer fragments and trace metal concentrations. All of these overlap with what natural processes also produce. The planet keeps the asteroid signature because it is distinctive. The planet dissolves the civilization signature because the chemistry is shared with nature. Nature's most catastrophic events leave unambiguous markers. Civilization's most extensive activities leave ambiguous ones. This asymmetry is not accidental. It reflects something fundamental about the relationship between industrial activity and natural geochemistry. Industrial civilization does not inject exotic elements from outside the Earth system. It recycles the Earth's own chemistry, burning carbon that was once atmospheric, releasing nitrogen that was once fixed in organic matter, extracting metals that were once distributed through crustal rocks. The materials we use are Earth's materials. When we release them, we are releasing them back into the system they came from. The system has seen all of this before, under natural conditions. It cannot tell the difference from 50 million years away. An asteroid is genuinely alien. Its iridium did not come from Earth's crust. Its shocked quartz required pressures that no terrestrial geological process produces. It's spherules formed from rock that was vaporized and resolidified in conditions that do not occur naturally on Earth's surface. The geological record recognizes the asteroid signature as foreign because it is foreign. The civilization's signature reads as domestic because, geochemically speaking, it is. Understanding this distinction changes what you expect the search for a prior civilization to find. You are not looking for something exotic and clearly artificial. You are looking for a recombination of Earth's own chemistry in proportions and timings that are slightly unusual. Slightly unusual is the territory of ambiguity. It is the territory of a dozen competing natural hypotheses, each plausible, each consistent with the evidence, none of them requiring industrial activity as a cause. And here's the deepest cut from Schmidt and Frank's analysis. The evidence that would most strongly suggest a prior civilization. A rapid carbon isotope excursion combined with a temperature anomaly, combined with an ocean acidification signal, combined with a biological extinction pulse, is exactly the evidence that already exists in the geological record attributed to natural events. The PTM, the Towarsian OAE, the End Triassic event. We are not waiting to find such an anomaly. We already have multiple examples. We have attributed them to natural processes. We may be right. We cannot be certain. The mechanisms of surface destruction work simultaneously and reinforce each other. Erosion strips expose surfaces continuously. Burial compresses lower layers under accumulating weight, generating heat and pressure that drive metamorphic reactions and destroy original texture. Plate tectonics subducts oceanic crust back into the mantle over tens of millions of years, melting everything within it. Continental crust is more stable but not immune. Mountain ranges rise through collision and are worn flat over tens of millions of years of erosion. A sedimentary basin that looks stable over human timescales is a temporary feature in geological terms. What makes the geological record feel more complete than it is? Partly the way we encounter it. Geology is taught through specific examples: the Jurassic Coast, the Grand Canyon, the Burgess Shale. These are places where unusual circumstances have preserved an unusual amount. They feel representative because they are famous. But famous geological sites are famous precisely because they are exceptional. The normal geological record is discontinuous, gap-ridden, chemically altered, and stripped of most of what was once present. The exceptions are not the rule. Consider what the geological record would show for our civilization if you sampled it randomly, rather than from the exceptional preservation sites. Most of the land surface of Earth is subject to active erosion. Over millions of years, the material currently sitting on exposed continental surfaces will be stripped, transported, and deposited somewhere downstream. The cities in mountain regions will erode first. The cities in coastal plains, which happen to be where most of the world's largest cities are located, will be buried under accumulated sediment if sea level rises or eroded if sea level falls, depending on the local tectonic history over the next few million years. The fraction of our civilization's material that ends up in an exceptional preservation environment is small. The fraction that ends up in such an environment in the end is sampled by a future researcher is smaller still. Random sampling of the geological record of our era 50 million years from now is likely to return no anomaly in most samples, a weak chemical anomaly in some samples, and a clear fly ash signal in a fraction of samples from appropriate depositional environments. The research analyzing those samples without a prior hypothesis will probably note the chemical anomaly as interesting, attribute it to a natural carbon event, and move on. The fly ash signal, if encountered, is the one marker that might cause her to pause and consider an alternative interpretation. But fly ash in isolation is not sufficient to establish a prior civilization. It suggests industrial coal combustion, but without corroborating evidence, the case for artificiality remains inconclusive. There is one more feature of the preservation problem that deserves explicit attention: the role of plate tectonics in creating age-selective gaps in the record. Oceanic crust is continuously created at mid-ocean ridges and destroyed at subduction zones. The oldest oceanic crust on Earth is roughly 200 million years old. Everything older has been subducted and melted. Continental crust is older and more stable, but large portions of the ancient continental record have been deformed, metamorphosed, or eroded beyond the point of useful chemical analysis. A search for a prior industrial civilization at 50 to 60 million years ago is working with Eocene-age sediments, which are relatively well preserved by geological standards. Ocean drilling programs have collected cores spanning this interval from multiple ocean basins. The material exists and is accessible. What has not happened is a targeted reanalysis of that material using Schmidt and Frank's diagnostic target list. The data may already exist. The question has not been asked of it. This is the position Schmidt and Frank leave the hypothesis in, not solved, not excluded, not even properly tested. Placed on the scientific table as a framework with specific observational targets identified, waiting for someone to look. The geological record of 50 to 60 million years ago is not a blank page. It is a page that has been read for one set of questions and not yet read for another. The Silurian hypothesis is an argument that the other set of questions deserves to be asked. This is not a counsel of despair. It is a description of what the evidence actually is, held honestly without inflation. The geological record of our civilization will be there in 50 million years. Parts of it will be readable. None of those readable parts will be sufficient on their own to establish what they came from. The total picture, assembled from all available cores and outcrop sections, might be enough to raise serious questions. Whether anyone will be in a position to ask those questions, whether there will be a technological civilization conducting geological research 50 million years from now, is a separate question that the Silurian hypothesis does not address, but implicitly depends on. The temporal scale of geological erasure is something human intuition is simply not built to process. We experience time in units of days, years, lifetimes. A century is old. A millennium is ancient. 10,000 years is the span of all recorded human civilization. These are the reference points that feel large to us. Against the 3.6 million year erasure window, 10,000 years is less than 0.3%. The entire span of everything we would call human history, from the first cities to the present, fits inside the erasure window roughly 360 times over. The 3.6 million year window is not the distant past. It is, in geological terms, almost the present. And even the almost present is beyond what the record can reliably identify as artificial. The KPG boundary layer illustrates what all this does to even catastrophic events. That thin stripe in the rock marks the end of the Cretaceous 66 million years ago, when an asteroid ended 3/4 of all species on Earth. The fires, the darkness, the acid rain, the ecosystem collapse, 10,000 years of cascading catastrophe. In the rock record today, the entire 10,000-year interval appears as a layer you can cover with your thumb. Dark clay, iridium anomaly, shocked quartz. That is what it looks like. That is what 10,000 years of planetary catastrophe looks like from 66 million years away. If you did not know what to look for, you would mark it as an interesting mineralogical anomaly and move on. The asteroid impact is actually the best case for detection, not the average case. An asteroid delivers a chemical marker, the iridium anomaly, that is distinctive, durable, and globally distributed. Iridium is rare in Earth's crust. Even small quantities stand out clearly above background. There is no natural process other than a large chondritic impactor that produces a sharp, globally distributed iridium spike in the sediment record. The signal is unambiguous. A civilization does not produce an iridium anomaly. A civilization produces carbon. It produces nitrogen compounds. It produces glass spheres and polymer fragments. All of these overlap with what natural processes also produce. The planet keeps the asteroid signature because it is distinctive. The planet loses the civilization signature because the chemistry is shared. Nature's most catastrophic events leave unambiguous markers. Civilization's most extensive activities leave ambiguous ones. And the geological record, which preserves what is distinctive and processes what is not, keeps the asteroid and loses the civilization. That is the foundation. Now here is what Schmidt and Frank actually did with it. Schmidt and Frank were not asking whether it happened. They were asking whether we would know. Most people encounter the name and reach the wrong conclusion immediately. The Silurian period ended 419 million years ago. Life then was aquatic and newly terrestrial, consisting of early fish, invertebrates, and the first vascular plants. No civilization existed during the Silurian. No civilization is claimed to have existed during the Silurian. The name comes from a 1970 episode of Doctor Who in which a reptilian species is described as Earth's original dominant civilization. Schmidt and Frank borrowed it not as an endorsement of that fiction, but as shorthand for the category of question they were formally asking. What if something sophisticated was here before us, and we cannot see it? The paper appeared in April 2018 in the International Journal of Astrobiology, a peer-reviewed publication associated with Cambridge University Press. Gavin Schmidt is the director of NASA's Goddard Institute for Space Studies. His research on paleoclimate reconstruction and climate model validation is cited across thousands of scientific papers. Adam Frank is a professor of astrophysics at the University of Rochester. He thinks seriously about the long-term trajectories of technological civilizations viewed as a class of planetary phenomenon rather than as a uniquely human one. Neither man published this paper carelessly. There is a specific test that Schmidt and Frank propose as the most productive target for a rigorous search. If a prior industrial civilization existed and produced a large enough carbon pulse, the resulting temperature anomaly and ocean acidification event should appear in the geological record at the relevant time interval. The search, therefore, is for isotopic carbon excursions that are anomalously large, anomalously shaped, or anomalously shaped compared to what natural processes can produce. The problem with this test is that it requires knowing what natural processes can and cannot produce, which requires models of those processes, which requires assumptions about boundary conditions that are not always well constrained for the deep geological past. This is not circular reasoning, but it is reasoning under uncertainty. The natural hypotheses for PEM-like events are calibrated against our knowledge of how volcanic carbon releases, methane hydrate destabilizations, and other natural mechanisms work. That knowledge is real and substantial. But it is also incomplete, and the incompleteness leaves room for the kind of ambiguity the Silurian hypothesis identifies. The question is not whether natural processes can produce carbon anomalies. They demonstrably can. The question is whether the specific quantitative characteristics of any given anomaly, including its magnitude, rate, duration, and isotopic composition, can be uniquely attributed to one mechanism rather than another. For the PTM and similar events, the answer is currently no. The characteristics are consistent with natural mechanisms. They are also consistent with industrial mechanisms, and the geological record does not have sufficient resolution to distinguish between scenarios that differ primarily in the speed of the initial carbon injection, which is exactly the parameter that most strongly separates industrial from natural sources. The central question is not whether a prior civilization existed on Earth. The central question is whether the geological record, as we currently understand and can read it, would be able to tell us if one had. The methodology begins with the present. Schmidt and Frank catalogued the signatures industrial civilization produces and asked, for each one, what its geological half-life looks like. How long before this particular trace becomes undetectable or ambiguous enough to be indistinguishable from natural processes that produce nearly identical results? They were not asking about soft signatures like cultural artifacts or written records, which dissolve in centuries under most burial conditions. They were asking about hard chemical and physical signatures, the kinds of things geochemists and sedimentologists actually measure when they study the deep past. Physical structures survive roughly 3-6 million years. Chemical signatures survive longer but carry a different problem. Isotopic anomalies in carbon and nitrogen can persist in the rock record for tens of millions of years, provided the sediments containing them are not metamorphosed or subducted. But their persistence comes at the cost of ambiguity. The same chemical signatures produced by industrial civilization are also produced by several well-documented natural processes. Carbon isotope excursions happen during volcanic episodes and during oceanic methane release events. Nitrogen isotope shifts occur during ocean anoxia and during certain types of microbial activity. The chemical fingerprint of industry overlaps almost completely with the chemical fingerprint of nature under certain conditions, and the overlap is not coincidental. Industrial civilization burns ancient biological material and adds it to the atmosphere. Ancient biological material is exactly what natural processes also release under certain conditions. The chemistry is similar because the source material is related. This is the first wall. The second wall is temporal resolution. The geological record does not preserve time with uniform fidelity. Deep ocean basins accumulate sediment at rates of a few millimeters per 1,000 years. At that rate, a century of time represents a layer perhaps 1/10 of a millimeter thick. Bioturbation, the physical mixing of sediment by burrowing organisms, operates over the top 10 to 20 centimeters of the sediment column. At deep ocean accumulation rates, that mixing homogenizes tens of thousands of years of time before the sediment is buried deeply enough to preserve its original layering. An industrial civilization that operated for 2 centuries would leave a chemical anomaly compressed into a layer the record cannot resolve individually from a natural event that unfolded over 20,000 years. The brevity that might in principle distinguish industrial activity from slower natural processes is exactly the feature that temporal smearing erases. The third wall is stratigraphic incompleteness. The geological record is not a continuous archive, it is full of gaps, unconformities, surfaces where erosion removed material before deposition resumed are present at every scale. Some represent brief pauses, others represent millions of years of missing time. In any given sediment core, some fraction of the geological record is simply absent, and the absence is not always obvious from the core itself. If a prior civilization existed during an interval now represented by an unconformity, the chemical signature would be missing from those cores entirely. Not ambiguous, gone. 3 independent walls, each fatal on its own. Together, they multiply. The only way to identify a prior civilization with confidence would be to find multiple anomalous signatures clustered in the same geological interval, each individually explainable by natural processes, but collectively forming a pattern statistically improbable as coincidence. This convergent evidence approach is how scientists confirm other complex geological phenomena. The KPG asteroid attribution required iridium anomaly, shocked quartz, spherules, global distribution of the boundary layer, and fossil turnover all converging. No single piece was conclusive, but geological processing tends to destroy clustering. As sediments are reworked over millions of years, as chemical diffusion blurs boundaries between layers, as different signatures degrade at different rates, the tight clustering of anomalies that would characterize an interval of industrial activity spreads and blurs. By the time the signatures have survived 50 million years, the simultaneous occurrence of multiple anomalies might be spread across a range of sediment depths wide enough to make the coincidence seem expected rather than significant. The convergent evidence has been uncoupled by time. Schmidt and Frank also address what might be called the observer problem. The scientists who study the geological record are trained on the natural processes that dominate Earth's history. When a geologist encounters an anomalous layer in a core, her first response, trained into her by years of education and practice, is to search for a natural explanation. This is not closed-mindedness. It is appropriate scientific reasoning. Natural processes are far more common than industrial civilizations in the geological record, so assuming a natural explanation is the rational prior. The entire interpretive apparatus of the field is oriented toward natural explanations and would need to encounter evidence of artificiality that was strong and unambiguous before departing from that orientation. The evidence a prior civilization would leave, as Schmidt and Frank carefully demonstrate, is not strong enough and not unambiguous enough to force that departure. There is a philosophical dimension to this that is worth naming. The hypothesis invites a kind of epistemic care that science does not always apply to its own conclusions. Scientists are trained to report what the evidence shows, and what the evidence for a prior civilization shows is nothing. The natural reading of that nothing is that there was nothing there. Schmidt and Frank are asking for a more careful reading, that the nothing is not evidence of absence but evidence of detection limits. These are different statements. One closes the question, the other keeps it open. Keeping questions open when the evidence does not justify closing them is a discipline that science applies rigorously in some domains and less rigorously in others. The Silurian hypothesis argues that this question belongs in the domain where the evidence does not yet justify closure. One of the most important features of the Schmidt and Frank methodology is that it is falsifiable in principle, even if it has not been tested in practice. A falsifiable question is a scientific question. The hypothesis predicts that a prior industrial civilization would leave a specific combination of chemical anomalies in the geological record. An isotopic carbon excursion of a particular magnitude and shape, elevated fly ash concentrations in the same geological interval, anomalous nitrogen isotope ratios, and possibly elevated concentrations of certain trace metals and persistent polymer residues. If a systematic survey of candidate geological intervals found none of these anomalies at levels above natural background, that result would meaningfully constrain the hypothesis. It would not prove the absence of a prior civilization because of the detection limits Schmidt and Frank document, but it would narrow the space of possibilities. The hypothesis is also falsifiable from the other direction. If such a systematic survey found a combination of anomalies that were statistically improbable as natural coincidence, that would constitute evidence worth investigating further, even if it fell short of proof. Science does not always require proof. It requires evidence that changes the probability distribution of what is true. The Silurian hypothesis is, at its core, an argument about the prior probability that should be assigned to the question of a prior civilization before any specific evidence is examined. Schmidt and Frank are arguing that the prior probability should not be treated as negligible, because the detection limits mean that the absence of detected evidence has less evidential weight than it appears to. The compounding barrier problem deserves more attention, because it is the feature that makes the detection failure robust rather than contingent on any single limitation. Consider what it would take to overcome each barrier independently. To overcome the physical erasure of structures, you would need to find a depositional environment where material from the relevant time interval was buried rapidly, protected from metamorphism, and preserved without distortion for tens of millions of years. Such environments exist, but they are rare and unevenly distributed across geological time. The probability that a prior civilization's built environment happened to be located adjacent to one of these exceptional preservation sites is low. To overcome the temporal resolution problem, you would need a sediment core from an environment with extraordinarily high accumulation rates, undisturbed by bioturbation, from a location that happened to be directly downstream of a major industrial center during the relevant period. Again, possible, not probable. To overcome the chemical ambiguity problem, you would need to find a combination of signatures in the same core that are collectively improbable as natural coincidence, using analytical methods with sufficient precision and isotopic resolution to distinguish industrial carbon from geological carbon at the level of detail required. This is perhaps the most tractable barrier in principle, but it requires knowing in advance that you are looking for a civilizational signature, which requires having the prior hypothesis that such a signature could exist. The observer problem closes the loop. Each barrier individually reduces the probability of detection. Together, they multiply. Our prior civilization could have left real chemical evidence in the rock record, and that evidence could be present right now in cores already collected and archived in repositories around the world, interpreted as natural chemical variation, filed correctly under the existing framework and never reconsidered. Schmidt and Frank note one more feature that most discussions of the hypothesis miss. The detection problem is asymmetric in a specific way. A large, long-lasting civilization leaves a larger footprint, and therefore has more chances for some fragment of evidence to survive, in at least anomalous form. A smaller, shorter civilization, one that perhaps collapsed quickly after a brief industrial period, leaves a smaller footprint and therefore has fewer chances. The civilizations that are hardest to detect are the ones that most resemble what a failed civilization would look like. Brief, intense, geochemically active for a century or two, then gone. This is precisely the scenario the hypothesis is most interested in, and it is precisely the scenario for which the detection probability is lowest. The methodology Schmidt and Frank developed is not designed to prove a prior civilization existed. It is designed to quantify what a rigorous search would require, and to assess whether such a search has ever been conducted. The answer to the second question is no. No systematic search has been conducted, because the question was never previously framed in a way that generated a search protocol. Existing geological data has been collected and analyzed to answer questions about natural climate variability, biological evolution, and tectonic history, a search for industrial signatures in deep geological time would require different target measurements, different sites, and a different interpretive framework. Schmidt and Frank argue it would be scientifically legitimate to conduct such a search. The search would either produce a null result that meaningfully constrains the possibility, or it would turn up anomalies worth investigating further. In either case, the science would be more informed than it currently is. The paper ends not with a conclusion, but with a set of observational targets. Specific isotopic measurements. Specific sediment core locations. Specific geochemical proxies that would be most diagnostic if an industrial signal existed. This is the hallmark of a genuine scientific contribution. It does not just pose the question. It tells you how to try to answer it. The fact that no significant investigation has followed in the years since the paper was published is itself informative. It reflects the same observer problem the paper describes. The question is not yet inside the standard scientific framework for this type of research, and questions that are not inside the framework tend not to get funded, studied, or published. The most important comparison case for what a prior industrial world would look like in the rock record is an event sitting 9 million years back in the geological sequence. It is one of the most intensively studied events of the past 2 decades of paleoclimate research, and its chemical structure, read carefully, looks almost exactly like what we are doing to the planet right now. The best evidence we have for a prior industrial civilization is also the best evidence for a natural warming event. That is the problem. The Paleocene-Eocene thermal maximum. Its abbreviation PEEE, thermal maximum, its abbreviation PEEN, is standard in the paleoclimate literature. Its basic features are discussed in most serious treatments of ancient climate. But knowing the outline is different from understanding what it actually looks like in the sediment cores. And that difference is the entire point of this section, 55.9 million years ago. The background climate was already substantially warmer than today. No permanent polar ice caps. Alligator relatives and subtropical vegetation in the Arctic. The global average temperature was stable and had been stable for a geologically extended period. Then, over a time frame the record describes as geologically rapid, something introduced a massive quantity of carbon into the ocean atmosphere system. Global average temperatures rose by 5 to 8 degrees Celsius. Ocean pH dropped as dissolved CO2 formed carbonic acid. Deep-sea benthic foraminifera, tiny carbonate-shelled organisms living on the ocean floor, experienced one of their largest extinction events in the geological record. 30 to 50% of species gone. On land, mammals diversified explosively. The ancestors of horses and primates appear in the fossil record for the first time near the PETM boundary. The event lasted approximately 200,000 years before the climate returned to its pre-perturbation baseline. In sediment cores, the PETM appears as a sharp negative excursion in the carbon isotope ratio. The heavier carbon-13 becomes less abundant relative to the lighter carbon-12. This matters because different carbon sources have different isotopic signatures. Volcanic carbon tends to be isotopically heavy. Carbon from biological sources, including ancient organic matter, fossil fuels, and microbially produced methane, is isotopically lighter because biological processes preferentially incorporate the lighter isotope during photosynthesis. The PETM excursion is light. The dominant hypothesis involves methane hydrates, ice-like structures of methane and water, stable under the specific temperature and pressure conditions found on continental shelves. A small initial warming, possibly triggered by orbital changes or volcanic activity associated with the opening of the North Atlantic Ocean basin, may have destabilized these hydrates, releasing large quantities of methane into the water column and eventually the atmosphere. Methane is a potent short-term greenhouse gas. Its atmospheric oxidation produces CO2. A methane hydrate destabilization cascade would explain the isotopic signature and would represent a feedback loop in which initial warming triggers additional carbon release. It is worth making explicit what Schmidt and Frank are and are not claiming about the PETM, because the distinction matters for understanding the hypothesis correctly. They are not claiming the PETM was caused by an industrial civilization. The existing natural explanations are plausible, consistent with the evidence, and represent the best current scientific understanding. They are claiming something more methodological and, in its own way, more important. that the chemical and isotopic record of the PETM cannot exclude an industrial cause using current analytical methods. These are not the same claim. The first would be a historical assertion about a specific geological event. The second is a statement about the capabilities and limitations of our detection methods, which applies regardless of what actually caused the PETM. The practical implication is that if we want to search for evidence of a prior industrial civilization in the geological record, the PETM and events like it are the correct place to look, not because they are suspected of being artificial, but because they are the kind of events that an industrial civilization would have produced. A systematic search would involve collecting high-resolution sediment cores from multiple locations spanning the PETM boundary, applying the full suite of geochemical proxies Schmidt and Frank identify as most diagnostic, and comparing the quantitative characteristics of the anomaly to predictions from both natural models and industrial models. This kind of search has not been conducted. The scientific community has been studying the PETM for decades, but always within the interpretive framework that assumes a natural cause. The question Schmidt and Frank are raising has never been formally tested against the existing data. The debate has not reached consensus. Different research groups using different isotopic correction methods and different sediment cores sometimes arrive at different quantitative estimates of the total carbon released and its rate. Other proposed causes include rapid oxidation of previously frozen organic matter, the combustion of large peak deposits, and some combination of sources acting in sequence. The existing natural hypotheses are plausible. They fit well enough that no one has been forced to look for alternatives. Here is the point Schmidt and Frank make that reorients how you read all of this. The time resolution of the geological record at 55.9 million years cannot distinguish between a carbon pulse that lasted a few hundred years and one that lasted 20,000 years. Sediment accumulation rates, bioturbation mixing, and chemical diffusion blur the sharp edges of events over geological timescales. What the record resolves as a 20,000-year event might have been a 2,000-year event with a longer plateau. What looks like gradual warming might have been a rapid spike followed by a slow decline. If an industrial civilization had emitted carbon at roughly the rate we currently do, for a duration of 2 to 5 centuries, and had then disappeared, the carbon pulse in the rock record at 55.9 million years would be indistinguishable from what we already observe. The isotope excursion would be there. The temperature anomaly would be there. The ocean acidification signal would be there. The ocean acidification signal would be there. The biological disruption would be there. And all of those features already have plausible natural explanations. Not because geologists are wrong, because natural processes can produce all of them. The rate problem is worth dwelling on, because it is where the industrial comparison is sharpest and most uncomfortable. Current human emissions are approximately 10 gigatons of carbon per year. The PETM carbon release, spread over its full duration of roughly 20,000 years, represents an average annual rate that is lower than current emissions by perhaps an order of magnitude. On its face, this comparison seems to argue against the industrial hypothesis. If our emissions rate is faster than the PETM rate, the PETM must have been natural, but the comparison is made incorrectly because the geological record cannot resolve the rate. The record sees the total carbon injected over an interval it cannot subdivide. If the PETM unfolded over 20,000 years at a slow natural rate, the record at 55.9 million years looks the same as if it unfolded over 200 years at an industrial rate, followed by 19,800 years of slower recovery. Temporal smearing makes these indistinguishable. The rate argument that seems to exclude the industrial hypothesis depends on the assumption that the record has resolved the rate. It has not. It cannot. This is not a hypothetical concern. The rate of the PETM's initial carbon injection is one of the most actively debated aspects of the event. Different research groups using different analytical methods and different sediment cores arrive at different estimates. Some papers argue the initial phase was faster than the dominant models suggest, potentially occurring over a few thousand years. Others argue for a more gradual progression. The debate continues because the data genuinely cannot resolve it at the resolution required to settle the question. The temporal blur is real, and it affects the most critical parameter for the industrial comparison. There is another feature of the PETM that Schmidt and Frank find particularly instructive: the asymmetry between the rapid onset and the much slower recovery. The initial warming phase was substantially faster than the 200,000-year recovery period. This asymmetry is characteristic of carbon cycle perturbations, driven by a rapid pulse of carbon input, followed by the slower silicate weathering drawdown. Industrial civilizations burning fossil fuels would produce exactly this asymmetric signature: rapid emission over centuries, followed by much slower removal over hundreds of thousands of years. A rapid natural pulse, whether from methane hydrate destabilization or from rapid peat combustion, would also produce this asymmetry. The asymmetric shape is consistent with industrial origin. It is not diagnostic of it. The geographic distribution of the PETM signal adds one more layer. The carbon isotope excursion at the PETM is recorded in sediment cores from every ocean basin and from numerous continental sections around the world. This global distribution is consistent with an atmospheric perturbation that mixed rapidly around the planet before being deposited in sediments at each location. Industrial fossil fuel combustion distributes carbon through the atmosphere globally. Large-scale volcanic carbon release also distributes globally. Localized geological processes, such as regional methane seep activity, would produce a more geographically restricted signal. The global distribution of the PETM signal is consistent with both large-scale natural releases and industrial activity. It does not help distinguish between them. The ocean acidification signal during the PETM adds another parallel. The dissolution of carbonate sediments in deep-sea cores across the PETM boundary reflects a drop in ocean pH driven by CO2 uptake. This is the same process currently occurring in today's oceans in response to human emissions. The PETM acidification event is already studied as a natural analogue for ocean acidification driven by industrial carbon emissions. Schmidt and Frank note that this parallel cuts both ways. The processes are similar because they are driven by the same fundamental chemistry, and that fundamental chemical similarity is exactly what makes the geological signatures indistinguishable. The silicate weathering feedback is worth understanding in more detail because it is one of the primary mechanisms by which the planet normalizes carbon perturbations over geological time, and it operates in the same way regardless of whether the carbon came from a volcano, a methane hydrate, or a fossil fuel burning civilization. When atmospheric CO2 increases, rainfall becomes more acidic. Acid rain weathers silicate rocks, a process that consumes CO2 and releases calcium and magnesium ions into rivers and eventually into the ocean, where they combine with dissolved carbonate to form calcium carbonate sediment. This process removes CO2 from the atmosphere at a rate that increases as CO2 increases, creating a negative feedback. Over timescales of tens of thousands to hundreds of thousands of years, this feedback restores the atmospheric CO2 to approximately its pre-perturbation level. The implication for the Silurian hypothesis is that the atmospheric signature of an industrial civilization, the elevated CO2, would be largely normalized by the silicate weathering feedback within a few 100,000 years of the civilization's collapse. What would remain in the rock record after this normalization is the isotopic anomaly preserved in the sediment deposited during the perturbation, not the current atmospheric composition. The sediment records the chemistry of the past. It does not update. This is why the PTN carbon excursion is still readable in cores from 55.9 million years ago. The chemistry of the ocean during that interval was recorded in the carbonate and organic matter that settled to the sea floor, and that record was subsequently buried and preserved. But the record is of the perturbation as it appeared during the anomalous interval, not as it appears now from the outside. This distinction matters for how we think about what a prior civilization's signature would look like. We would not be looking for elevated atmospheric CO2, which has long since returned to background levels. We would be looking for a brief interval in the sediment record where the carbon isotopes were lighter than surrounding material, where the temperature proxy indicators suggested warming, where the ocean chemistry indicators suggested acidification, and where the biological record suggested a pulse of extinction and recovery. All of these features are present in the PETM. All of them have natural explanations. None of them require an industrial cause. And Schmidt and Frank's point is that none of them exclude one either. The full weight of the PETM section of the Silurian hypothesis is this. If you constructed a geological record of what an industrial civilization would do to a planet, and then compared it to what actually happened 9 million years ago, the comparison would be close enough that you could not exclude either explanation using current methods. The natural explanation is more probable because natural events are more common than industrial civilizations, but more probable is not the same as confirmed. The PETM is the geological record's best candidate for what a prior industrial era would look like, and the geological record has already explained it away. Schmidt and Frank do not argue the PTM was caused by a prior industrial civilization. That is not their claim. What they argue is that the PTM is the kind of event that a prior industrial civilization would have produced, and that, given current detection capabilities, we cannot distinguish between those two scenarios from the chemical and isotopic record alone. Consider what a researcher does when she encounters the PTM in her cores. She has a set of well-developed natural hypotheses. She constructs models of each proposed mechanism and tests them against the isotopic data and the temperature record. The methane hydrate scenario fits reasonably well. The volcanic scenario explains some features but not the full magnitude of the excursion. A combination factors fits better than any single one. At no point in this analysis does she consider the possibility that the carbon excursion was produced by an industrial civilization burning fossil fuels. Why would she? Industrial civilizations have not previously been part of the interpretive framework for Eocene geology. The existing hypotheses do not consistently fail. They fit well enough that no one is forced to look for alternatives. This is not a failure of scientific reasoning. It is the way science works. But it means the interpretive framework has a blind spot. The PEEM could have an entirely natural explanation, and probably does. What the chemical evidence cannot do is distinguish between a natural explanation and an industrial one, and that distinction has never been explicitly tested because the question has never been formally posed. The carbon cycle illustrates another feature of the detection problem: how Earth systems normalize perturbations over geological time. Carbon released during the PETM was eventually removed through silicate weathering, a slow process in which CO2 reacts with exposed rock to form carbonate minerals that settle to the ocean floor. This negative feedback operates over timescales of tens of thousands to hundreds of thousands of years, and eventually brings atmospheric CO2 back toward its pre-perturbation level. The same feedback would remove the signature of an industrial civilization from the atmosphere over geological time. The system returns to a state that looks natural because it is natural. The perturbation has been processed and absorbed. What remains in the record is the snapshot of the anomalous interval, compressed by time, sitting in the sediment like a question without a label. The PEN discussion in Schmidt and Frank's paper ends with an important admission. They cannot determine whether the PEEM was caused by a prior industrial civilization, and they are not claiming it was. What they are claiming is that the current state of geological knowledge cannot exclude it. That is a much weaker claim than it might appear. It does not require accepting that a civilization existed. It requires only accepting that the geological record, at the resolution available to us, cannot rule out what it cannot detect. The PETM is the test case. If the test case cannot be resolved using the best available methods, then the broader question of whether any prior industrial civilization existed anywhere in Earth's deep history cannot be resolved using the best available methods. That is the core conclusion of the hypothesis, and it is methodological rather than historical. The PETM is not alone. The Torsian oceanic anoxic event 183 million years ago shows a rapid carbon isotope excursion and an associated pulse of marine extinction. The N-Triassic extinction 201 million years ago has a carbon anomaly associated with massive volcanic activity from the Central Atlantic magmatic province, but the rate and timing of carbon release in that event are still debated. Several Cretaceous oceanic anoxic events show rapid carbon and oxygen anomalies, with causes that remain subjects of active research. None of these events has a fully agreed-upon explanation for every feature of its isotopic record. Each is a candidate signal in the sense Schmidt and Frank define, not because they are likely to be industrial in origin, because they are the kind of event that would be left by an industrial civilization. and because current methods cannot rule that interpretation out with the rigor science requires for confident exclusion. We have signals in the geological record. We cannot determine what generated them. That problem does not resolve with more data from the same record. It resolves, if it resolves at all, with a fundamentally different category of evidence, which raises the question, what category of evidence would be strong enough? What does our civilization actually leave behind that a future geologist with the right tools and the right prior hypothesis might be able to identify as artificial? The answer to that question is more specific and more uncomfortable than most people expect. In 50 million years, the entire Anthropocene will be a layer of sediment 3 centimeters thick. Picture a geologist in the deep future, on a continent reshaped by 50 million years of tectonic movement. She is pulling rock cores in a region that, in our time, was somewhere in what we call the Northern Hemisphere. The surface above her has been through several glacial cycles, multiple sea level transgressions and regressions, and the slow grinding erosion that removes kilometers of material from any landscape over sufficient time. She is searching for a boundary layer, a chemical anomaly her research group has been tracking across multiple continental sequences. She finds it at a depth corresponding to the late Cenozoic, a thin dark stripe, maybe 3 centimeters, maybe 4. She marks it. She labels it as a probable volcanic carbon event based on the isotopic signature. She photographs the core. She moves on. She does not know because there is nothing in the core that tells her that the layer she just marked contains the compressed chemical remains of every city, every road, every factory, every landfill, every aircraft, and every human being that existed during a period spanning roughly 2 centuries. She cannot know this because the layer does not look like those things anymore. It looks like elevated carbon, glass spheres, a trace anomaly in certain hydrocarbons. She has the right instruments. She has the right training. She just does not have the prior hypothesis that this could be artificial, because nothing in her training told her to consider that possibility. This is not a hypothetical future scenario constructed for rhetorical effect. This is the Anthropocene, described accurately from the perspective of deep geological time. The scenario is built from what we know about geological preservation rates, sediment compaction, chemical diagenesis, and the specific properties of the materials our civilization produces. It is worth going through the components of that future layer carefully, because the exercise shows exactly which parts of our civilization leave durable evidence and which parts dissolve back into the geological background. Start with concrete. Humans currently produce roughly 40 billion tons of concrete per year. That figure exceeds the total annual sediment load carried to the oceans by all the world's rivers combined. We are manufacturing rock-like material at a rate that rivals natural geological processes. By volume, concrete is the single most manufactured solid material in human history, exceeding steel by roughly a factor of 30. Modern Portland cement concrete is artificial sedimentary rock. Its chemistry is distinct from natural limestone or sandstone in specific and measurable ways. Under burial conditions, concrete undergoes a predictable sequence of degradation. Carbonation, where groundwater CO2 reacts with calcium silicate hydrates to form calcium carbonate, progressively alters the chemistry of the binding matrix. Sulfate attack from groundwater minerals corrodes the aluminum phases. Under burial pressure, the pore structure compresses and the original structural integrity is lost. The chemical residue remains in the sediment. A geochemist with the right instruments might flag the calcium silicon chemistry as unusual. But unusual chemistry has natural explanations. Volcanic ash altered by groundwater. Biogenic silica concentrated by diagenesis. Without a prior hypothesis that the unusual chemistry might be artificial, the most parsimonious interpretation is always natural. Steel tells a simpler story. Iron is one of the most abundant elements in Earth's crust and one of the most geochemically mobile. The iron in steel structures, once oxidized, enters the surrounding sediment and groundwater as ferric and ferrous ions. These redistribute through aquifer systems, precipitate in oxygen-poor zones as iron sulfides and iron oxides, and become indistinguishable from the iron that natural weathering contributes continuously to every sedimentary environment. The steel industry produces roughly 1.4 8 billion tons of steel per year. At geological timescales, all of it will have returned to geochemically ordinary iron phases in the sediment, leaving no distinguishable artificial signal. Nothing. Microplastics are the most interesting case, because synthetic polymer chains do not occur in nature. No natural process produces polyethylene, polypropylene, polystyrene, or the dozens of other polymer types now present in every sediment-forming environment on the planet. Ocean floor sediments contain them. Arctic lake cores contain them. They are being incorporated into the sedimentary record of the Anthropocene at a global scale, beginning sharply around 1950. In this specific sense, plastics represent the clearest artificial marker in the geological record of our era. The question is how long they remain recognizable as artificial. Under burial, UV degradation stops, but biological and chemical degradation continues at reduced rates. Common high-volume plastics like polyethylene and polypropylene break down into simple hydrocarbon chains that at geological timescales enter the sediment organic carbon pool and become chemically indistinguishable from natural organic matter. Some resistant polymer types may preserve their distinctive chemistry for longer, but the quantity of resistant polymers in total global plastic production is small relative to the high-volume commodity plastics that dominate by mass. The microplastic signal in the geological future is more likely to appear as a faint and ambiguous hydrocarbon anomaly than as an unambiguous artificial marker. Fly ash is different. Coal-fired power generation produces spheroidal carbonaceous particles, smooth, hollow, glassy spheres of aluminosilicate composition produced when the non-combustible mineral fraction of coal passes through a high-temperature furnace and is cooled rapidly. The specific morphology, spherical, hollow, glassy, with a particular size distribution and elemental composition, is produced only by high-temperature coal combustion. Wildfires produce irregular charcoal particles with rough surfaces and variable composition. Volcanic eruptions produce ash with irregular morphology and a different chemical signature. There is no natural process that produces smooth, glassy aluminosilicate spheres with the specific composition of coal-derived fly ash. These particles are already used in sediment core studies as unambiguous markers of industrial coal burning. A core from a lake anywhere in the northern hemisphere that shows a sharp increase in spheroidal carbonaceous particles at a certain depth can be competently associated with the onset of industrial coal use in that region. Under burial conditions that avoid high heat and pressure, fly ash spheres may preserve their diagnostic morphology for geological timescales. Some fraction of the Anthropocene's fly ash layer may still be recognizable 50 million years from now in sediment sequences that escaped metamorphism. If fly ash is the strongest marker, then what the Anthropocene leaves behind is a layer of material dominated by chemical ambiguity, with one category of physically distinctive particle that might survive geological time in recognizable form, embedded in a matrix of isotopic anomalies and hydrocarbon concentrations that a future researcher would reasonably attribute to a natural carbon release event. The thought experiment of the 3 cm layer repays extended attention because it is not just a description of what happens to buildings and roads, it is a description of what happens to information. Every physical record of our civilization encodes information, the content of books, the configuration of electronic systems, the structure of institutions, the accumulated scientific and cultural knowledge of 10,000 years of human intellectual activity. All of that information is encoded in physical media. Physical media is subject to the same geological processing as everything else. Paper decomposes in decades. Electronic media decomposes in centuries. Stone inscription survives in geological terms but is subject to erosion and metamorphism over millions of years. At 50 million years, no readable record of human intellectual activity survives in any physical medium. This is a separate point from the chemical signature question. Even if a future geologist identified the Anthropocene layer as artificial, she would have no access to any of the content of our civilization. The 3 centimeters of chemically anomalous sediment would tell her that something industrially active existed here. It would tell her approximately when, within the resolution of the geological timescale. It would tell her something about the scale, from the carbon anomaly and the fly ash distribution. It would tell her nothing about what we thought, what we valued, what we built, what we lost, or why we existed. The geological record is a record of quantities and chemistry. It is not a record of meaning. The meaning of our civilization, whatever that is, does not enter the rock. It stays here in the brief interval of time we occupy and dissipates with us. Future geology will know we existed in the same way it knows a volcanic episode existed, from the chemistry of what was released, not from the content of what was built. The nitrogen signature is worth adding to the picture because it represents a category of marker that differs from the carbon story in an important way. The Haber-Bosch process, which produces synthetic ammonia from atmospheric nitrogen and underlies all modern agricultural fertilizers, fixes nitrogen with a slightly different isotopic signature from biologically fixed nitrogen. Industrial nitrogen moves through agricultural soils and into river and ocean systems at a scale sufficient to leave a detectable imprint in sediment records from the past century. The isotopic anomaly is real and measurable now. Whether it survives 50 million years at a level distinguishable from natural nitrogen cycling variations depends on the diagenetic history of the sediment and the precision of the isotopic measurements available to future researchers. Natural nitrogen isotope excursions occur during ocean anoxia events and during certain types of microbial activity in sediment-poor waters. The artificial nitrogen signal, even if it survives, must be distinguished from these natural sources. The same overlap that affects the carbon record affects the nitrogen record. The signatures exist, but they are not exclusive to industrial civilization. Rare earth elements present a similar story. These metals, used in electronics, catalysts, and advanced materials, are distributed through industrial effluent in concentrations above natural background in sediments near manufacturing centers. Certain rare earth element anomalies are already used in sediment studies as traces of industrial activity at the resolution of decades. At geological timescales, the rare earth signatures redistribute through the sediment as the enclosing rock is altered by diagenesis and groundwater flow. Some fraction of the anomaly survives. Whether it remains spatially concentrated enough to be distinctive from natural hydrothermal or volcanic rare earth enrichments is uncertain. Lead, from centuries of leaded fuel and paint, is elevated in lake sediments worldwide, and has been since the Roman period, which represents a pre-industrial but still human-driven anomaly in the record. Lead isotope ratios can distinguish smelting-derived lead from natural geological sources with some confidence at short timescales, because different ore deposits have distinctive isotopic signatures. At geological timescales, the isotopic signal persists longer than the concentration anomaly, but interpreting it as artificial requires the prior hypothesis that artificial lead sources existed. The exercise of going through all of these signatures has a cumulative effect that is more important than any individual entry. What emerges is a picture of a civilization whose chemical footprint is real and measurable at the present moment, becomes ambiguous within tens of millions of years, and becomes indistinguishable from natural variation within 100 million years. The Anthropocene is leaving marks. The marks are not permanent in any meaningful geological sense. They are leaving faint chemical traces in the sediment record that a well-equipped future geochemist could detect but could not confidently attribute to artificial sources without a prior reason to look for them. Schmidt and Frank also make an observation about scale that cuts against naive optimism about our detectability. Our civilization is large, it is global. It processes energy and materials at rates that are, by historical standards, extraordinary. If a future geologist were specifically searching for evidence of a civilization in the Anthropocene layer using Schmidt and Frank's list of target signatures, she would probably find anomalies worth investigating. The signal is strong enough to detect in principle. The problem is not that the signal is too weak. The problem is that no one is searching for it as a civilizational signal. Every anomaly in the Anthropocene layer is being interpreted, correctly given the existing framework, through natural explanations. The signal is present and it is being systematically explained away, not because the explanations are wrong, but because they are also right. This is the most precise statement of the detection problem. The evidence of a prior civilization would not be absent from the geological record. It would be present and correctly explained as something else. If you are finding this kind of depth worthwhile tonight, a subscription or a like helps this channel keep making content like this. It is a small action that makes a genuine difference for whether work like this reaches more people. The isotopic carbon excursion from fossil fuel combustion will be present in the Anthropocene layer and will be readable. Current human emissions are approximately 10 gigatons of carbon per year. If emissions continue at elevated levels for a century or two before declining, the total carbon pulse will fall in the range that the record at 50 million years will compress into something indistinguishable from several known natural events. The isotope anomaly will be there. It will be interpretable as a natural carbon release. A careful geologist might note that the apparent rate of change seems unusually fast even by natural standards. That note will likely be filed as an interesting anomaly rather than a sign of industrial activity. Radioactive isotopes from nuclear weapons testing are completely unambiguous, artificial markers for our era. Plutonium-239, cesium-137, strontium-90 do not occur in nature at the concentrations that weapons fallout produced. Cesium-137 has a half-life of 30 years. Gone in centuries. Plutonium-37 has a half-life of 30 years. Gone in centuries. Plutonium-239 has a half-life of 24,000 years. Gone in a few 100,000 years. On the timescales, the Silurian hypothesis addresses, the entire nuclear signature of the 20th century is long dissolved. The cumulative picture, a real, measurable, multi-component chemical signature. Not nothing, not invisible, but filtered through 50 million years of geological processing, the composite reads as an unusual but not impossible combination of natural anomalies. The fly ash particles are the strongest artificial marker. The microplastic residues are a weaker secondary marker. The isotopic carbon excursion is present but shared with natural events. The physical structures are gone. The radioactive isotopes are gone. What remains is a few centimeters of chemically unusual sediment that a future researcher would, rationally and correctly, explain through the framework of natural processes available to her. The exercise of cataloging what survives and what does not has a clarifying effect on how you think about durability. We tend to evaluate the durability of our civilization by looking at what has survived from earlier civilizations. Roman concrete, Egyptian stone, Mesopotamian fired brick. These are the things that impress us because they survived long enough to be found and examined. But they are not representative, they are the exceptional fraction. Most of what Rome built is gone. Most of what ancient Egypt built is gone. Most of what Mesopotamia built is gone. What survives is what happened to be made from materials resistant enough and buried in conditions favorable enough to persist to the present. Our civilization will be treated the same way by geological time. The fraction that survives will be the fraction that happened to be made from resistant materials and happened to be deposited in exceptional preservation environments. The fly ash that settles in lake sediments and ocean basins. The chemical anomaly in the isotopic record of those sediments. A small fraction of microplastic residues in the most chemically stable sedimentary environments. These are the survivors, not the cities, not the institutions, not the languages, the chemical byproducts. What the Anthropocene layer actually records is the heat and the carbon and the glass spheres. It records the energy we burned, not what we burned it for. We are not building for the future. We are building for the sediment. The cities compress into chemistry. The roads dissolve into altered mineral phases. The languages leave no mineral trace. The art and institutions and accumulated knowledge of 10,000 years of civilization, none of it enters the rock record in a form that announces its artificial origin from 50 million years away. The sediment keeps almost none of it, and the little it keeps, it does not label. If we cannot find a prior civilization on our own planet, we had no hope of finding one across the galaxy. Here is where the Silurian hypothesis stops being about geology and becomes something larger. Here is where the question underneath the question surfaces. The Fermi paradox is one of the defining unresolved problems in modern scientific thinking. Enrico Fermi raised it during a 1950 lunch conversation at Los Alamos with a simple question. If intelligent life is common in the universe, where is everybody? The Milky Way galaxy is roughly 13.5 billion years old. Stars capable of supporting life have existed for most of that span. A civilization that began expanding at 1% of the speed of light could traverse the entire galaxy in less than 10 million years. 10 million years is a geological eye blink. There have been hundreds of millions of years during which such expansion could have occurred. And yet, as far as our instruments can determine, there is nothing. No unambiguous radio signals, no megastructures, no interstellar probes in our solar system. The silence requires explanation. The scientific literature contains dozens of proposed explanations in three broad categories. Either intelligent life is extremely rare, perhaps uniquely so, or civilizations arise but consistently fail to reach interstellar capability. Or something else is happening that we do not understand. None of the proposed solutions is comfortable. Adam Frank has written about this problem extensively and has identified a connection to the Silurian hypothesis that is not immediately obvious, but is, once you see it, difficult to unsee. The standard framing of the Fermi paradox treats the absence of detected signals and artifacts as meaningful evidence about the rarity of intelligent life. The logic runs, if civilizations were common, we would detect evidence of them. We have detected no unambiguous evidence. Therefore, civilizations are rare. This logic is reasonable, but it depends on an assumption that deserves examination. It assumes our detection methods are adequate, and the Silurian hypothesis demonstrates, with geological rigor and quantified detail, that our detection methods are inadequate even for civilizations on our own planet. Think carefully about what that means. We have full physical access to Earth's geological record. We have been studying it systematically for 2 centuries. We have a global network of research programs, drilling operations, sediment core archives, and analytical laboratories. We have instruments capable of detecting isotopic anomalies at parts per trillion concentrations. We have the full body of geological and geochemical theory developed over 200 years of careful observation by thousands of researchers across every continent. And despite all of that capability, Schmidt and Frank showed that we could not confidently identify the geological signature of a prior industrial civilization if one existed 50 million years ago. The noise is too similar to the signal. The time resolution is too coarse. The chemical ambiguity is too fundamental. Now apply the same reasoning to the electromagnetic search for extraterrestrial intelligence, where the detection problem is incomparably harder. We are looking for signals across interstellar distances of tens to thousands of light years through the noise of an electromagnetically active cosmos, with instruments designed to detect specific signatures that we have decided based on our own technology are the most likely to be used by other civilizations. Radio telescope searches cover a tiny fraction of the sky at any given time. Optical searches for laser pulses face similar limitations. Infrared surveys for megastructures or Dyson spheres are more comprehensive in sky coverage, but assume a specific type of energy harvesting strategy. Frank's argument is not that the universe is teeming with hidden civilizations our searches have missed. His argument is that the absence of detections tells us less than we have assumed. If detection methods are inadequate for the geological record of our own planet, they are certainly inadequate for the electromagnetic record of the galaxy. The Fermi silence is partly a detection problem, not purely an existential or sociological one. We are reading absence as evidence when absence may simply be the limit of our instruments. The Drake equation is the standard framework for organizing estimates of the number of technological civilizations in the galaxy. Frank Drake proposed it in 1961. It multiplies a series of factors: rate of star formation, fraction of stars with planets, fraction of habitable zone planets developing life, fraction developing intelligence, fraction developing intelligence, the Rayfing-to-Leverking technology, and the lifetime of a technological civilization. We now know most stars have planets. Habitable zone planets are common enough that there may be billions in the Milky Way alone. The later factors, particularly the lifetime of a technological civilization, are almost completely unconstrained by observation. Frank has argued that the lifetime factor has been systematically underestimated in its uncertainty. The standard calculation assumes that if civilizations have long lifetimes, they would be detectable. But if detection is harder than assumed, long-lived civilizations might exist without being detectable. The Silurian hypothesis provides a concrete, quantified example of how hard detection can be even in the most favorable possible case. If that detection problem is as hard as Schmidt and Frank show, the detection problems at interstellar distances must be assumed to be far harder. The Drake equation as typically applied assumes a level of detection capability that the Silurian hypothesis suggests we do not have. Frank and collaborators have developed this thinking into a research program they call galactic archaeology. If civilizations leave geological and chemical signatures in their home planets, and if those signatures can be specified in advance, it may eventually be possible to search for them remotely in other planetary systems. Not by listening for radio signals, by analyzing the atmospheric and surface chemistry of distant planets for anomalies consistent with industrial activity, isotopic carbon excursions, microplastic analogues, fly ash equivalents. The geological fingerprints of technological civilization, searched for across interstellar distances. The James Webb Space Telescope has begun measuring exoplanet atmospheric compositions with unprecedented sensitivity. Future telescopes will go further. Frank argues that industrial signatures should be explicitly included in the search targets for those telescopes, alongside biosignatures of microbial life. The Silurian hypothesis, by forcing a precise characterization of what industrial activity looks like in the geological record, provides part of the scientific foundation for that work. There is a symmetry in the detection problem that Schmidt and Frank note carefully. If we cannot rule out a prior civilization on Earth from our full access to the geological record, then a civilization elsewhere in the galaxy cannot rule out prior civilizations on their own planet either. Every technological civilization that has existed faces the same wall of geological noise when looking backward in its own history, and the same wall of distance and instrumental limitation when looking outward. The universe may contain civilizations that cannot find each other and cannot find their own predecessors. Both of them, perhaps, staring at the chemical record of their planet, finding ambiguous anomalies, constructing natural explanations for them, and being right to do so. Both of them unable to know what they cannot know. There is a category of search that the Silurian hypothesis suggests has been systematically undervalued. The search for extraterrestrial intelligence has historically focused on signals that a civilization would deliberately send, narrowband radio transmissions designed to be recognized as artificial against natural backgrounds, laser pulses timed to attract attention, beacon signals structured to announce intelligent origin. The underlying assumption is that a civilization capable of interstellar communication would choose to communicate and would design signals specifically to be recognized. This assumption may be correct for some civilizations in some eras. It is not necessarily correct for all civilizations in all eras. Civilizations might use communication technologies that produce no electromagnetic signature recognizable to us. They might have moved beyond electromagnetic communication entirely. They might have chosen silence for reasons we cannot currently conceive, or they might simply not exist in sufficient numbers or proximity to produce signals we can detect with current instruments. Frank's galactic archaeology program suggests a different category: passive detection of the geological and atmospheric signatures that civilizations leave as a side effect of their existence, without any deliberate effort to be detected. A civilization burning fossil fuels alters its planet's atmosphere in specific ways. A civilization building at scale alters its planet's surface chemistry. These passive signatures require no deliberate communication. They are the unavoidable byproducts of the energy use and material processing that define technological civilization, and they might be detectable in principle in the spectra of exoplanet atmospheres measured by future telescopes, if the instruments are sensitive enough and researchers know what to look for. The Silurian hypothesis, by forcing a precise characterization of what industrial activity looks like in the geological and atmospheric record, provides a scientific foundation for specifying what those passive signatures should look like at interstellar distances. This is not currently possible. The instruments required do not exist. But the trajectory of the field points toward increasing capability. The question Frank raises is whether industrial signatures should be added explicitly to the list of search targets for future telescopes. The answer, he argues, is yes, not because finding them is likely, but because not looking for them guarantees not finding them. There is one more dimension of the Fermi paradox that the Silurian hypothesis illuminates: the question of civilizational lifetime in the context of geological detectability. Frank and collaborators have developed what they call the Anthropocene equation, an attempt to characterize the long-term trajectory of technological civilizations using thermodynamic principles and the history of Earth's biosphere as reference points. One key finding is that civilizations that manage to develop sustainable energy systems and avoid destabilizing their planetary climate may persist for much longer than civilizations that fail at this transition. But a civilization that persists by becoming sustainable is a civilization that reduces its chemical and thermal anomalies over time. It burns less fossil fuel. It produces less carbon. Its geological signature shrinks. This creates a paradox for detection. The civilizations most likely to survive long enough to become detectable across interstellar distances are the civilizations that have reduced their detectability by becoming sustainable. The civilizations that leave the strongest geological signatures are the ones that failed the transition and collapsed after a brief industrial period. The fossil record, in a deep sense, preferentially preserves the civilizations that did not make it. The survivors are the ones hardest to find. Or there may have been only one. There may have been a dozen. There may have been thousands scattered across the galaxy's history, each rising and falling and leaving signals too faint or too ambiguous to detect from any other location. The geological record of Earth and the electromagnetic record of the galaxy, taken together with the best methods currently available, cannot distinguish between these possibilities. There is a way of thinking about the Fermi paradox that the Silurian hypothesis enables, but that most treatments of the paradox do not reach. Most treatments focus on the question of whether civilizations exist. The Silurian hypothesis focuses on the question of whether civilizations are detectable and shows that the two questions are not the same. A universe in which civilizations exist but are largely undetectable from each other would look, from inside any given civilization, almost identical to a universe in which civilizations are rare. The observation space available to any single civilization is too small, in both time and extent, to distinguish between these scenarios with confidence. This is not a new idea in the Fermi paradox literature. The concept of civilizations being electromagnetically quiet, or the concept of civilizations operating in ways we do not recognize as technological, has been discussed for decades. What the Silurian hypothesis adds is a concrete, quantified demonstration of how detection can fail even in the easiest possible case. Looking for a civilization on your own planet with full physical access to the rock record. If the easiest case fails, the hard cases should be expected to fail even more thoroughly. The Fermi silence is, at minimum, partially explained by detection limits. How large a part of the explanation detection limits are is unknown. But the part is real and is larger than most treatments of the paradox acknowledge. The Fermi paradox is sometimes treated as a problem with a solution, one that will be revealed once we either detect an alien signal or definitively establish that intelligent life is rare. The Silurian hypothesis suggests a different framing. The Fermi paradox may not have a solution in the conventional sense, because the detection methods available to any technological civilization may be structurally inadequate for answering the question it poses. Not because technology is insufficient, but because the universe processes information in ways that make certain questions unanswerable from within the temporal and spatial constraints that any civilization occupies. Every civilization exists for a finite time at a specific location. During that time, it can accumulate evidence about events within its detection range. Events outside that range, whether separated by distance or by time, leave traces that attenuate and are processed by intervening natural systems before they arrive. The Silurian hypothesis is a specific, quantified case study of how badly a trace can attenuate over geological time, even when you are standing on the very planet where the event occurred and have full physical access to the rock. The lesson generalizes. Detection is hard. Absence of evidence is not evidence of absence. And the universe may be far more populated with the history of civilizations than any currently living civilization can determine. This is not a comforting conclusion in the sense of confirming that we have neighbors. It is a comforting conclusion in the sense of establishing that we cannot rule out that we do. The silence of the galaxy, like the silence of the geological record, may be a silence of detection limits rather than a silence of emptiness. Both of them saying the same thing. You cannot know this from where you are standing. Look harder. Ask better questions. Accept that some questions outlast the civilizations that ask them. That is not a failure of science. It is an honest accounting of what the evidence can and cannot support. Which is where you find yourself tonight, at the end of this particular thread. The story of life on Earth has always been told as a long, unbroken chain. That phrase from the beginning of tonight carries more weight now than when you first heard it, because what Schmidt and Frank showed, working through the numbers with geological precision, is that the chain is not something we can verify as unbroken. It is something we assume is unbroken because the breaks, if any exist, are invisible. The rock record does not preserve the chain. It preserves chemistry. And the chemistry, at the timescales that matter, is not enough to reconstruct what produced it. The chain we see is the chain the rock agreed to keep. Everything the rock decided not to keep. Everything it processed and transformed and recycled back into the crust over millions of years is represented in the record only by silence. And silence is ambiguous. It can mean nothing happened. It can mean something happened and the evidence dissolved before we arrive to look. What the Silurian hypothesis asks you to sit with is the specific character of that ambiguity, not the dramatic version where a lost civilization concealed its existence from the future, the quiet version which is stranger and more unsettling, where an industrial civilization, if it existed, would have left exactly the kinds of evidence we already have, and we would already have attributed that evidence to natural processes, and we would be right to do so. There is no conspiracy in the rock. There is only the ordinary operation of geological time, which does not distinguish between the artificial and the natural when it compresses them both into the same sediment layer over millions of years, 3.6 million years. Schmidt and Frank's physical erasure window. The entire span of the genus Homo, every human ancestor that walks upright and eventually built cities and wrote languages, fits inside that window. Everything we are building right now will enter the geological record as chemistry. The future geologist pulling cores through our era will find a thin anomalous stripe and will, rationally and correctly, reach for the simplest natural explanation. Because that is what the scientific method asks of her. Because natural processes can explain what she finds. Because she has no prior reason to suppose it could be artificial. The specific kind of uncertainty the Silurian hypothesis describes is worth naming precisely, because not all uncertainty is equivalent. There is the uncertainty of not having looked hard enough, which resolves with more effort. There is the uncertainty of having the wrong tools, which resolves with better instruments. And there is the uncertainty of asking a question that the available evidence is structurally incapable of answering, regardless of how much effort is applied within the existing framework. The Silurian hypothesis argues that the question of a prior civilization is in the third category, not because geology is inadequate as a science, but because the timescales involved exceed the preservation capacity of physical structures, and because the chemical signatures involved overlap with natural processes in ways that current analytical methods cannot resolve. Recognizing this kind of structural limitation is not pessimism. It is the precondition for asking better questions. Schmidt and Frank asked a question that generated a research protocol. The research protocol specifies what measurements would be most diagnostic. If those measurements were conducted systematically, the uncertainty would not necessarily resolve, but it would be better characterized. The uncertainty might narrow to a specific time interval, a specific chemical ratio, a specific combination of signatures that is either present or absent. That narrowed uncertainty would be worth more than the current broad uncertainty, even if it did not produce a definitive answer. Schmidt and Frank cannot tell us whether the hypothesis is true. They cannot tell us whether the rock record is hiding something or simply recording accurately the history of a planet that has had only one technological civilization in its 4.5 billion years. They cannot tell us whether the PEN was natural or artificial. What they can tell us, with precision and rigor in a peer-reviewed paper, is that we do not know. Not as a vague confession of uncertainty, as a specific quantified statement about the limits of our detection capability applied to a specific class of question. We do not know whether something was here before us. Schmidt and Frank gave the question a scientific framework. They did not answer it. They clarified what answering it would require. And what answering it would require is evidence that the geological record with its current resolution and its current interpretive framework is not equipped to provide. That might change. Future methods might achieve finer temporal resolution in specific sediment environments. Future interpretive frameworks might explicitly include industrial signatures as a class of hypothesis to be tested against anomalous geological intervals. Future researchers might systematically survey the rock record for the specific combination of signatures Schmidt and Frank identified as the most robust markers of industrial activity. If any of that happens, the question might move from open and unanswerable to open and actively being investigated. That would be progress, not toward a confirmed answer, but toward a more honest accounting of what the geological record can and cannot tell us about what came before. That honest accounting is the actual contribution of the Silurian hypothesis, not a claim about ancient history. A claim about epistemology, about the limits of what can be known from the evidence available to us, about the distance between what the record shows and what actually happened. The hypothesis lives in that distance, and the distance is real and large and rarely acknowledged. What it means to be the first civilization on a planet that cannot remember whether it had one before is a question that sits outside geology. It sits outside physics. It sits in the space where science hands the question to something else and says, this far and no further. The rock cannot answer it. The sediment cannot answer it. The chemical anomalies we call the PETM and the Torsian OAE and the N-Triassic event cannot answer it. They are silent on the question that matters most, not because they are hiding something, but because the geological record does not hold what geological time erases. The long, unbroken chain is still the most likely story. The probability that a prior industrial civilization existed and left no recoverable evidence is not high. A civilization that persisted for any significant duration would have left a larger and more distributed footprint, and a larger footprint provides more chances for some piece of evidence to survive in at least anomalous form. The hypothesis is not that a prior civilization is probable, it is that it is not excludable. And not excludable means the question stays open. What you carry out of tonight is a cleaner understanding of what the geological record can and cannot say. It cannot say the chain is unbroken. It can say it found no evidence of a break. Those two statements are not equivalent. The difference between them is the entire space the Silurian hypothesis occupies, not in the rock, in the silence between what the rock remembers and what actually happened. What it means to be the first civilization on a planet that cannot remember whether it had one before is a question the geological record cannot answer. Maybe that is enough to know. Maybe that specific kind of uncertainty, held honestly, is its own kind of beginning. The planet has been here for 4 or 5 billion years. Technological civilization has existed for perhaps 200. The ratio is 22, 5 million to 1. Even if technological civilizations are relatively common in the history of life-bearing planets, any given civilization spends only a tiny fraction of its planet's lifespan as a technological entity. The window during which a civilization is producing detectable geological signatures is brief. The window during which those signatures remain distinguishable from natural processes is briefer still, and the window during which another civilization exists simultaneously and has the tools to detect them is another improbable coincidence layered on top of the first two. The Silurian hypothesis is not a comforting document. It does not offer resolution. It offers clarity about the limits of what can be resolved, and clarity about limits, held honestly, is a form of knowledge worth having. It tells you where the ground ends. It tells you what you are standing on when you make confident claims about the past. It tells you that the silence you read as emptiness might be silence for reasons that have nothing to do with emptiness. What it means to be the first civilization on a planet that cannot remember whether it had one before is a question the geological record cannot answer. Maybe that is enough to know. Maybe holding that specific uncertainty honestly, without forcing it into a comfortable resolution it does not have, is its own form of clarity. The rock does not owe us an answer. It only owes us what it actually holds, and what it holds is ambiguous in ways that matter, for reasons that are precise. About a question that stays open. The chain continues. 3 centimeters. Maybe 4. That is what the planet keeps. That is what geological time, which is patient in a way that has no human equivalent, decides is worth preserving from 2 centuries of industrial civilization. The rest returns to the cycle. It becomes the sediment from which future rock forms. It becomes the chemistry of future oceans. It becomes the atmosphere of a future era that does not know what it is. Breathing was once a city, or a highway, or a power plant, or a life. The geological record is not a record of what existed, it is a record of what the planet decided to keep. Those are not the same thing, and the difference is where tonight has lived. The silence in the rock is not empty, it is full of things the rock chose not to keep. We just cannot see where it.